In this video, I want to prove one of the results of the algebraic limit theorem, or as I like to abbreviate it, the ALT. If a sequence a sub n converges to a real value a, c times a sub n, which is, you can imagine multiplying all of our terms in our sequence by some number c, converges to c times a, the limit also multiplied by c. In other words, if we scale a sequence by c, if we multiply all the terms in the sequence by c, the limit is also going to be scaled by that same c. Before we go into the proofy stuff, we need a more formal definition of convergence, right? The definition of convergence is for all epsilon greater than 0, there exists an in of epsilon such that for all n greater than n of epsilon, we have that a sub n minus a is less than epsilon. Most textbooks don't include this, but I like to write n explicitly as a function of epsilon. Why is that? Because n is, at the end of the day, dependent on epsilon. One natural question you might have when learning about sequences and limits is, sure, a sub n might converge to a, but what happens if I, scale a, multiply all the terms in a by some number like c? What's going to happen to the limit? I kind of gave it away, but let's see this visually, right? I don't know, scaling up our sequence by multiplying by positive 3. We get this. By multiplying by minus 2. So all of our terms in our sequence are multiplied by minus 2. And notice our limits, which are represented by these dashed horizontal lines. These are also scaled up by the appropriate values. Let's consider a sequence a sub n, which converges to, I don't know, like a. And let's consider a scaled version of that sequence, c times a sub n. Today we're going to show this converges to c times a. One way we're going to do this is to consider some, region around our limit, this region epsilon plus a and minus epsilon plus a. So let's first assume that our original sequence, which I've got down here, converges to a. Meaning for all positive epsilon, for all epsilon greater than 0, there exists some n of epsilon, some natural number n of epsilon, such that for all n greater than n of epsilon, the absolute value of a sub n minus a is less than epsilon. To prove this result of the algebraic limit theorem, essentially I need to show that there exists some natural number such that, c times a sub n minus c times a is less than epsilon. This is saying that eventually this scaled up sequence, c times a sub n, ignore this right there, cross this out, c times a sub n is eventually within epsilon of our scaled up limit, c times a. With some algebraic manipulation, I might notice, hey, I can factor out a c. I get c times a sub n minus a is less than epsilon. The absolute value of the product is the product of the absolute values. So this is the same thing as the absolute value of c times the absolute value of a sub n minus a. And this is less than epsilon, okay. I might divide by c. I get a sub n minus a is less than epsilon over the absolute value of c. For c not equal to 0, since we can't divide by 0, right? But again, since we're dealing with the absolute value of c, we're allowed to, not change. We don't have to change the inequality sign. This might seem familiar. You might be getting some deja vu from this. Why is that? Well, this comes back to our original sequence and its convergence. We know that, again, for all positive epsilon, we can find some natural number that will give us this inequality here. Okay. Well, why don't we use that same natural number, that same magical n, for this new sequence? Let's choose n of epsilon over the absolute value of c. And this means that for all n greater than n of the absolute value, n of epsilon over the absolute value of c, we have a sub n minus a is less than epsilon over the absolute value of c. This is based off the fact that this original sequence will get epsilon over c close to its limit. However, cleverly, we can actually multiply both sides of this inequality by the absolute value of c and derive the fact that this scaled up version of our sequence also converges. Specifically converges to CA. So okay, that's all fun and games, but how do we write this as a formal proof? Something we might see in a textbook or something we might be expected to do on a test in a real analysis class. Well, here's what a typical proof might look like. We have, here's our assumption, right? Let a sub n be a sequence of real numbers converging to a, and let k be a real number. In this case, k is going to be kind of like our c from earlier. A sub n converging to a, immediately I'm like, okay, let me write this more formally, right? For all epsilon greater than 0, there exists some n of epsilon, such that for all n greater than n of epsilon, we have the absolute value of a sub n minus a is less than epsilon. Cool. And we have two cases here based off the fact that we couldn't divide by 0 earlier. So let's get this out of the way. When k is 0, then k times our limit, doesn't matter what that limit is, it's 0. K times a sub n is 0 for all n, all natural numbers n. In other words, all of our terms multiplied by 0 is 0. The conclusion follows immediately, right? We get a sequence of just zeros. All of our sequence terms get canceled out to 0, and clearly this converges to 0, which is k times our original limit. More interestingly, though, what happens if k is not equal to 0? So let's let epsilon greater than 0 be arbitrary. Since a sub n converges to a, there exists some n of epsilon over the absolute value of c, and that's what we did our pre-work for. There exists some natural number n of epsilon over the absolute value of c such that, let's go back to this definition of convergence, for all n greater than n of epsilon over the absolute value of c, we have that a sub n minus a is less than the absolute epsilon over the absolute value of c. Let's multiply both sides by the absolute value of c. I get absolute value of c times a sub n minus a is less than epsilon, so epsilon is greater than this. Well, this is the same thing as c times a sub n minus a, because the product of the absolute values is the absolute value of the product. And if I distribute that a, or excuse me, I'll distribute this c right there, I can conclude that c times a sub n minus c times a is less than epsilon. And that's all I had to show, right? Since we assumed epsilon was arbitrary, it's true that for all epsilon greater than 0, we found a natural number n, which definitely exists. We found this n such that for all n greater than this magical big N, epsilon over the absolute value of c, ca sub n minus ca is less than epsilon. Therefore, in both cases, the limit as n approaches infinity of c times a to a sub n is equal to c times a. And we have proven one of the results of the algebraic limit theorem. Thank you for watching.